Welcome back to College Algebra, where we are looking at refreshing our memories on previously learned content. So we're now ready to move into solving quadratic equations. So take a look at the notes and we'll break down the techniques that we are going to be using in this section. First things first, you want to keep in mind the importance of factoring out any leading coefficient or dividing out any leading coefficient. Essentially, if our leading coefficient is a -1, we want to make sure that we divide that out of every single term, okay? And then, of course, if you have a GCF, a numeric GCF, we're going to divide that out of every term as well, okay? It's easier to deal with a reduced equation with smaller coefficients than, say, the original equation if we leave it as is. So we always want to make sure that we're preparing our quadratic equation effectively. As a reminder, we have the formula ax squared plus bx plus c equals 0. So this is our quadratic equation in standard form. Now, in terms of your methods for solving quadratic equations, the methods we have learned so far are to factor and use a zero factor property, right? You factor the actual equation, set it equal to 0, and then you solve. You can use the square root property. Now consider the only way you can use the square root property is if you have a squared expression equal to a constant. You'll then take the square root of both sides without forgetting the fact that you need to introduce a positive or negative in front of the square root on the right-hand side. We can also complete the square, which then allows us to use a square root property. We'll go through the motions of completing the square, but remember that what you're doing is you're cutting your linear term in half, that coefficient, your b. You're cutting that in half, you're squaring it, and then you're adding it to both sides. So essentially, you're going to prepare this equation such that it looks like the square of a binomial equal to a constant. That's the whole point, right? So essentially, you prepare your equation by bringing the constant over to the right-hand side, so it's no longer equal to 0 potentially. And then you take that b, cut it in half, square it, and add it to both sides. That will allow you to complete the square, writing it as the square of a binomial, and then you take the square root of both sides. And then, of course, please do not forget the positive and the negative. Lastly, you can also use a quadratic formula. You know your coefficients, A, B, C, and then you'll plug that directly into your formula. You'll either have to solve for exact values by simplifying, or you can essentially solve for an approximate value. And you'll actually know that in the software itself, whether or not it says, hey, give me the solutions or the zeros or the x-intercepts by using the quadratic formula, and then rounding to the nearest whole number, to the nearest tenths, etc. So those are the case where we can actually just plug it into our calculator and pull out a value. If they want exact values, you essentially want to take your quadratic formula, simplify as far as you can, separate into two terms, right? Your first term plus or minus your second term, and reduce if possible. That also means if that square root can be simplified, you need to do it as well. So for instance, if you had something like the square root of, I don't know, 20, we can rewrite that and we can break it down, okay? Square root of 20 breaks down into 2 square roots of 5. That should be a refresher, or essentially that should be a process that you're very comfortable with. Anyways, let's see this in action. Okay. The first things first, we are going to solve by the square root property, and then we're going to solve by factoring, just to show both of those techniques. So if we want to use the square root property, we have to isolate the squared term. So we're going to do that by bringing over the 125. We almost have the squared term by itself. Notice that we can take this one more step by dividing by 5. That leaves us with p squared is equal to 25. I have a squared term equal to a constant. I can now take the square root of both sides because the opposite of square is square root. We take the square root of both sides. We don't forget to introduce that positive and that negative. And that will leave us with p is equal to positive or negative, and then of course the square root of 25 is 5, since that is a perfect square. And those are your solutions. We're going to do this again, except I'm going to prove that that's the answer by factoring. So first things first, we have a GCF. I'm going to factor out 5. That leaves me with p squared minus 25 is equal to 0. Notice here, I have the difference of two squares. We learned in our factoring section that we would write that as p plus 5 times p minus 5, and that's equal to 0. I can divide both sides by 5 to eliminate this 5, or we can simply say any factors containing a variable get set equal to 0 and we solve. So that's the zero factor property. So that means we set p plus 5 equal to 0 and p minus 5 equal to 0, and then we solve. I subtract 5. That gives me p is equal to negative 5. I add 5, and that gives me that p is equal to positive 5. So two different methods, and I found the exact same solutions, of course, which you would have expected. Let's go ahead and turn the page. For number 2, we have n squared minus 12n minus 45 equals 0. So we're going to solve this by completing the square. First things first, we're going to move the constant term over to the right. That'll leave us with n squared minus 12n. I'm going to leave a little bit of a gap here because we want to actually complete the square, and I'll show you how we do this. You are going to take your b coefficient, right? Your b, the value of b. In this case, it's going to be negative 12. So you're going to take b, you're going to cut it in half, and then you're going to square it. So I'm going to show that process here. Take negative 12, divide it by 2. That's going to give me negative 6. Then we square it. Anytime you square this value, it will always be positive. If you accidentally plug this into your calculator without parentheses, it'll say negative 36, but we know when you square when you square negative, it becomes positive. So this should be a positive 36. Now this value here gets added to both sides. What you do to one side, you're going to do to the other. That way you keep this equation completely balanced. The cool thing about what we just did here is that we just created a perfect square trinomial. So if I went ahead and I factored this, this would actually become n minus 6 times n minus 6, right? Because negative 6 times negative 6 is a positive 36, and negative 6n and another negative 6n give us negative 12n. So we can rewrite this as the square of a binomial. N squared becomes n, right? Because we're looking at the factored form. And then I want you to notice something very interesting. We have parentheses with a square in it. So we're going to go over to where we have parentheses with a square in it, but we're looking for the simplified version, and that is negative 6. So whatever you see inside here in the parentheses will also go inside here in the parentheses. But that should also make sense, especially considering what we just described. The fact that if we were to factor this trinomial, it would become n minus 6 times n minus 6, or rather, n minus 6 quantity squared equals. Now we can add these two together. 45 and 36 give me 81. Now that I have a squared expression equal to a constant, I can use the square root property. So we're going to take the square root of both sides. Don't forget to include that positive and negative in front of that square root. The square root and the square cancel. That leaves you with n minus 6 is equal to positive or negative. And then, of course, the square root of 81 is 9. And that's because 9 times 9 is 81. We're almost done. I need to solve for n. So I have to add 6 to both sides. What that means is we are left with n is equal to 6 plus or minus 9. We always like to have that positive or negative in front, or excuse me, in between the two terms. So that means my two solutions are 6 plus 9 which is 15, and then 6 minus 9, which is negative 3. And those are your two solutions. For number 3, we're going to go ahead and use the quadratic formula. Now, I want you to take a look at this expression. It is not in standard form. So I'm going to begin by bringing the 21 to the left-hand side of the equals. Bring it over towards your other terms. Now we have 2x squared minus 11x minus 21 is equal to 0. Let's identify our coefficients, our a, b, and c. A in this case is 2. Notice I did not say 2x squared. It's just the coefficient. B in this case is negative 11. And then c is our constant, which is negative 21. Our quadratic formula follows this. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. We are now going to plug in and simplify. So x is equal to negative 11 is positive 11 plus or minus square root of. Now we have negative 11 squared, but negative 11 squared is 121 minus. Now we have 4 times a times c. I'll go ahead and write that. 4 times a, which is 2, times c, which is negative 21. All over 2a. 2 times 2, which is 4. So far, so good. I'm now going to take my calculator, and I'm just going to compute the discriminant. The discriminant is essentially our radicand. It's the quantity underneath the radical. As you recall from your previous semester, the discriminant will tell you if you have 2 real solutions, 1 double root, meaning 1 solution, or 2 complex solutions. Because our value is positive and it's greater than 0, we're going to have 2 real solutions. So let's rewrite this. We have x is equal to 11 plus or minus the square root of 289 all over 4. Let's see if we can take the square root of 289. Perfect. This becomes 11 plus or minus the square root of 289 is 17. That's because 17 times 17 is 289 over 4. Now, I'm going to split this up into 2 fractions. My first one is 11 plus 17 all over 4. So 11 plus 17 over 4. Let's do the math. This is going to become 28 divided by 4, and 28 divided by 4 is 7. There's my first solution. Next, we have 11 take away 17 over 4. If we simplify this, it gives us a negative 6 over 4, but we can reduce that to negative 3 over 2. And 7 and negative 3 halves are our 2 solutions. Those are our zeros, which can also be known as our x-intercepts. Perfect. Okay. This second part of our notes allows us to use the method of our choice. So essentially what we're doing here is we're looking at the equations we've been given and we're trying to say, well, what would be the best approach for something like this, right? Sometimes factoring is a lot quicker than, for instance, using the quadratic formula. So if we can factor, we should, right? So there are certain techniques you want to play around with. Check to see what you're comfortable with, and then also decide what makes the most sense. Okay, with that being said, this is a great place to pause the video. Try 4 and 5 on your own. Come back and let's see if we get the same answer, even if we use different techniques. Let's take a look. Okay, when I look at something like this, immediately I'm thinking, let's set this equal to 0, right? We should always think standard form. So I'm going to subtract 8k and bring that to the left. That means I have k squared minus 8k is equal to 0. The next thing I'm going to do is I'm going to say, well, I can factor out a k. So let's start there. So bring k out, that leaves me with k minus 8 is equal to 0. And then I can actually solve this. So factoring was the method of choice. Each factor containing a variable will get set equal to 0. So this k here by itself gets set equal to 0. That's my first factor. My second factor is k minus 8. So we're going to set that equal to 0. We go ahead and solve, and we find the two solutions. K is equal to 0 and k is equal to 8. And that's it. We're done. For number 5, I think about the idea of factoring, and I say to myself, well, are there factors of 19 that combine to give me 14? And that answer is no, because 1 times 19, if I subtract them, I get 18. So that won't work. I could bring the 19 over and then use the process of completing the square, or I can use the quadratic formula. So those two are my possible techniques. For the sake of playing around with completing the square, because I actually personally enjoy it, I'm going to use that method. So let's go ahead and start by adding the 19. We bring that over. We have a squared minus 14a, leave a little gap, and that's equal to 19. We are going to take our b term, we're going to cut it in half, and then we're squaring it. Let me write here that I'm completing the square. By the way, if you use a quadratic formula, you and I will have the same result. So let's see if you end up with the same answer. B is a negative 14. So we want to cut negative 14 in half. That's going to be negative 7. And negative 7 squared is a positive 49. We recall our result will always be positive. Okay, I went ahead and I added it to both sides, right, to keep the equation balanced. So now I can express this trinomial, this perfect square trinomial, as the square of a binomial. And that's going to be a minus 7 squared is equal to, and then we have 19 plus 49 is going to be 68. Beautiful. Now I have a squared expression, so let's go ahead and take the square root of both sides. Square root of the left, square root of the right. I won't forget that positive or negative right in front. The square root and the square cancel each other out. They are opposites. So we have a minus 7 is equal to positive or negative. Now I'm going to punch in the square root of 68 in my calculator just to do a quick test. Look at that. We cannot take the square root of 68, but maybe I can simplify this. So let's do a little bit of side work. With the square root of 68, let's see if there are any perfect squares that divide evenly. So what I'm going to do here is I'm going to test 68 divided by 4, because 4 is a perfect square. Now, the great thing is it did work out. So that means the square root of 68 can be rewritten as the square root of 4 times the square root of 17. So with that being said, I can actually take the square root of 4, and that becomes 2. So instead of writing square root of 68, I'm writing the simplified version. So that means we would write 2 square roots of 17. Cool. I'm one step away. I'm going to go ahead and add 7 to both sides. And now I'm going to write my answer. A is equal to, remember, keep this term first, then the plus minus followed by the term that you already had. So we have 7 plus or minus 2 square roots of 17. And those are your solutions. All this means is if we actually wrote this out, solution number 1 is 7 plus 2 square roots of 17, or 7 minus 2 square roots of 17. By the way, if your online homework manager said, hey, can you give me the answer to the nearest tenths? We would do 7 plus 2 square roots of 17. Go ahead and close it, and then we press enter. That means this first result is approximately 15.2. If we go ahead and scroll up, change that plus to a minus, press enter again, And now we found our second root, which is negative 1.2 approximately. Okay, these are our exact answers. So be careful. It depends on what the software is asking you. Excellent. Let's go ahead and turn the page. This is another great place. Pause the video, try 6, 7, and 8. Now that we've kind of got the juices flowing and we've looked through several problems so far. So we'll try these on our own and then you can check to see how you did. So take a look at what we see here in case you don't have the notes directly in front of you, but now you actually have the visual. Okay, let's get after it. For number 6, I'm going to bring the 5 to the left so that this is in standard form. So let's go ahead and subtract 5 on both sides. So this will leave me with 9m squared plus 18m minus 13 is equal to 0. I'm looking across the board and I don't see any GCF. At first I was thinking, ooh, maybe we'd end up with like a 3 or something and we could factor that out. But negative 8 and a negative 5 is a negative 13, so no such luck. Now, with that being said, in no way do I want to use completing the square. That means I would have to divide every term by 9, which will leave us with a nasty fraction here. So instead, I'm just going to say, you know what? Quadratic formula. Let's go. Let's make life easy. So typically we would write x equals and then negative b plus or minus, etc., etc. But our variable is m. So we're going to write m equals. Okay, that's the only difference. So our independent variable is m, so we've replaced x with m. But everything else is the same. Okay, so negative b is 18. So we have negative 18 plus or minus square root of b squared. I always like to just punch this in. So 18 squared is 324 minus 4 times a, which is 9, times c, which is negative 13. Let's extend that a tiny bit. And then we have all over 2 times a, and 2 times 9 is 18. Okay, let's go ahead and punch in the discriminant and see what we got here. So we have 324. Let's bring this over so you can see it. 324 minus 4 times 9 times negative 13. And that gives me 792. So let's go ahead and rewrite this. So I have m is equal to negative 18 plus or minus the square root of 792 all over 18. Can we take the square root of 792? Let's check it out. Oof, no, we cannot. Let's see if we can simplify this. 792 divided by 4. There's a 198. Let's see if that's divisible by 4 again. No, not quite. So what we may want to do with a problem like this is we want to actually look at the factors of 792 and see if we can find the greatest perfect square factor. So I'm going to take a moment to break this 792 down and I'll report back. Give me just 2 seconds. Okay, what I've chosen to do is essentially create a factor tree. So I took 792 and I divided by 2. That left me with 2 times 396. I broke down 396 again, 2 by 198. I broke down 198 again, 2 by 99. And then as soon as I saw 99, I thought, well, 9's a perfect square, so it's going to be 9 times 11. Now, I want you to notice 2 times 2 times 2 times 9 times 11 will give us 792. But 2 times 2 is 4, perfect square. 9, perfect square. So 4 times 9 is also a perfect square. So when I put these together, 4 times 9, which gives me 36, my other factor is 22. And you can double check that. You can punch it in to make sure that that's accurate. 36 times 22 is 792, where 36 is the largest perfect square factor. So that becomes 6 square roots of 22. All right, let's replace square root of 792 with this expression. So we have m is equal to negative 18 plus or minus 6 square roots of 22 all over 18. We only have one step left, and that is to rewrite this as 2 fractions that we can reduce. So here's how it works. m is equal to, your first fraction is negative 18 over 18. Then we have plus or minus, and now we have 6 squared to 22 over 18. Keep in mind both terms in your numerator are being divided by 18, so we have to split it up this way. And now that we do, we can actually reduce this. So negative 18 divided by 18 is negative 1, plus or minus, and 6 goes into 18 3 times. So this 6 becomes a 1, this 18 becomes a 3, which leaves me with square root of 22 over 3. So these are my solutions. Negative 1 plus square root of 22 over 3, and then negative 1 minus square root of 22 over 3. And we're done. Take a look at number 7. Number 7's cool because we see here, wait a second, we have some perfect squares, and we're thinking, ooh, can I use the difference of two squares? No, we have to stop right there. Notice we have a positive here. It's not a negative. So we do not have the sum of two squares. We only have the difference of two squares in terms of a factored formula. Not a big deal. All that means is I'm actually going to use the square root property, and I'm going to do that by bringing the 25 over first. Boom. Now I have 4p squared is equal to negative 25. I have to get my squared term alone, so I'm going to go ahead and divide by 4. That leaves me with p squared is equal to negative 25 over 4. Now I can use the square root property. So we're going to take the square root of both sides. Please do not forget that plus or minus in front. The square root and the square cancel each other out. And that leaves me with p is equal to positive or negative. Now recall that when you take the square root of a negative number, you actually have an imaginary number. So we're going to go ahead and pull out I in front. And then I'm going to take the square root of 25 and the square root of 4. The square root of 25 is 5. The square root of 4 is 2. And this looks messy, so I'm going to rewrite my answer. So p is equal to positive or negative 5 halves I. And we're done. Notice that this is in the form of a plus bi. So essentially this is 0 plus or minus 5 halves I. So a plus bi form, which is similar to a minus bi form, same exact thing. So this is what we're actually looking for. Can you graph this on a real number line? No. On a real coordinate system? No, you cannot, and that's okay. This just implies that if we were to graph this quadratic equation, which is a parabola, it would either be above the x-axis and it doesn't go through the x-axis, or it would be below. Because my leading coefficient is positive, it's going to be a u. So that means if I were to graph it, it's going to be floating above. So it's going to be somewhere like this, okay, where it does not go through the x-axis. So the roots are imaginary. Cool. One last problem. B squared plus 4b plus 5 is equal to 0. I mean, we can't factor. There are no factors of 5 that add up to give you 4. That won't work. So we could either use the quadratic formula, or we can complete the square again. I'm going to complete the square because we have on this page using the quadratic formula. So let's keep it exciting. So that leaves us with b squared plus 4b, leave a little gap, is equal to negative 5. Take that b divided by 2 and then square it. So 4 over 2 squared, that's 2 squared, which is 4. We're going to add that to both sides. Plus 4, love it. We rewrite this perfect square trinomial as the square of a binomial. So this becomes b plus 2. Remember that positive 2 here in the square, And that's going to be equal to negative 5 plus 4, which is negative 1. Let's take the square root of both sides. Put the plus or minus right in front. The square root and the square cancel, so it's b plus 2 is equal to positive or negative. Well, this is cool. The square root of negative 1 is I. That's literally the definition. If you forgot that, the square root of, excuse me, I is the square root of -1. This is just something you should keep in mind. This was from last semester when we talked about complex numbers. Cool. One final step, we need to isolate b. So we bring 2 over by subtracting it. And our final answer is b is equal to -2 plus or minus I. A plus or minus bi form. This is perfect. Those are your solutions. Again, if you were to graph this, it would be floating above the x-axis somewhere where the roots are imaginary. And that, again, is totally okay. And with that being shown, you're ready to practice solving quadratic equations. Make sure you go into your refresher central block, that's your practice block in your online homework manager, and go to town. Let's see how you do. Hope this helps. Bye.